finite degree.
Yeah, thank you. I'm Lukas. I should say I've given this talk before at a Lean Workshop earlier this year, which was organized by Jesse, which was very nice. But still, I'm gonna take a little bit of a different focus in the end, also because I don't have time for live coding today. So there should be something new for everyone, even if you've seen the previous talk. All right, where do I come from? I work in the field of, or like in the intersection of the fields of database theory and knowledge representation. And I'm working mostly with the so-called chase algorithm on so-called existential rules. And I think everybody in this area should formalize their work more. So I'm trying to lead by example and started a repo with that. So the rules that we have might just look a little bit like that. And you can read this as if I have an R, X, Y, then I should also be able to find a Z such that I have an R, Y, Z, or I just simply have R of Y, X. So this is just a fragment of first order logic, which is pretty simple and also very similar to data log. If you've seen a talk by Johannes, you notice a little bit already. All right. And now what the chase does is it takes an initial set of facts, or in this case, we just take a single fact, and then it tries to build up a model by just satisfying the rule iteratively. And we can do this and build something which we call a chase branch, or we could also call it a chase sequence. So we start with the fact RAB, and then we try to apply the rule, and we basically have two choices which side of the disjunction to consider. For example, first, we might want to use the left-hand side. So there should exist a Z such that we have R, Y, Z. And for this to be true, we introduce a fresh element, which we call N1, and introduce the corresponding fact. And now we've satisfied the rule for the RAB, but we don't satisfy it yet for the RB and 1. So we have to apply it again. And maybe now we want to choose the right-hand side and introduce the R and 1B. And once we do that, the rule is satisfied for every fact that we have here, so we're done. But as you can see, we could do this in different ways, right? It depends on whether we choose the left-hand or right-hand side. So what we usually do is combine all of that into what we call a chase tree. And for this example, this is going to be infinite because we can always keep on introducing new elements on the left-hand side. All right, this is a little bit where I'm coming from. And now what I need to be able to formalize this is some way of representing infinite trees in Lean, in this case, in the first place. And this is pretty much what the rest of the talk is going to be about. All right, so you might ask, maybe you don't if you know co-induction already, but you might ask, why not just use an inductive tree, right? So you could very straightforwardly define an inductive binary tree like this in Lean. But the problem with this is that the inductive definitions always give you only a least fixed point. So those would only give you all the finite binary trees. So this is not quite enough for what we want to do. And we want the greatest fixed point instead. So we want a big set of trees which adhere to this definition, basically, which can be destructed in that way, which includes the infinite ones. And this would be co-inductive. And while we might get co-inductive types in Lean in the future, we don't have them quite yet, so we have to be a little creative on how we approach this. All right, so the plan of attack for this small thing is to first take a hint from infinite lists, then see how we can make those infinite lists into possibly infinite lists, right? So they might also be finite. And then we're going to take this approach to build possibly infinite trees. And we also want those to have finite degrees because this is what our chase trees look like. Then we're going to define branches of such trees properly because this is also something that I need. And then for a little bit of playing, we are going to prove Koenig's lemma on those trees, which is stated like this, at least a special case for trees. I think you can state this more generally on graphs. But for trees, it just says, if each branch of a tree with finite degree is finite, then there are only finitely many branches in that tree. And this is something we want to show, not just for fun, but because we also want to consider some termination behavior of the chase algorithm. There, this is very useful to have. Okay. So let's talk lists at first. This is still pretty simple and actually in Mathlib, but there it's called stream prime. I think I saw on Zulip that there's currently some discussion going on of maybe renaming this into something else. But the idea there is just you can basically represent an infinite list of elements by just having a mapping from the natural numbers into the desired type. And for the sake of this talk, I will not call it stream prime, but just infinite list. Right. So how can we make this possibly infinite at first? And I think what you might think about first is just to use infinite list option alpha instead, which I think is okay, right? But there might be a problem with that. And I actually take the easy way out there and basically use that as a basis, but I also want a condition to hold, namely that this thing doesn't have any holes, right? So I don't want to have a lot of nons in between the actual elements of that infinite list. And this is just something stated in the second row, basically. So if something is not none, then everything which comes before is also not none. And this works out sufficiently well, and I'm happy with that. All right. And now we need to turn this thing into a tree. And the question is how? And once you see it, I think it's kind of easy, but I'm not sure if it's obvious. Maybe it is. Then it's nice. But the key idea is to change the address of the elements that we're talking about. So you can basically imagine the list as every element indexed by just a natural number. And now we could think about what would this index be in a tree. And basically in an infinite tree, we can index every element by a finite list of natural numbers. And this is just what we're going to do. So for our possibly infinite tree with finite degree, the basis is just a mapping which takes a list of natural numbers and maps this into an option of the actual type of the tree. This is like for the possibly infinite list we just saw, this is not enough. We need a bunch of extra conditions to make this kind of well-formed. And for this, I brought an example to you. So I'm basically always showing you can see the mouse, right? Yeah. Basically always showing the address list right here from left to right to make it more natural to read, even though in reality it's the other way around because it's right, you know. But so this is the address. In the root we just have some number, for example. So this would just be a tree over natural numbers. And then in the other nodes, we also have the addresses, and some of them might just not have a value. And now there's a couple of conditions. Similar to the no holes thing, we don't want any orphans right here. So everything should have a parent if it's not none. Then also the lists in one level should have no holes, right? And to make this also finite degree, we just demand that each node must have a child which is none. Okay. And this is good enough. And now we can define branches on that thing. Right. And we are going to do this for a little more general tree, which is not finite degree, but it just works the same way. And we call this a possibly infinite tree, abbreviated as PIT, and possibly infinite list as PIL to make it fit nicer on the slide. We're also going to start from the end. So once we have the possibly infinite tree, we want the branches to be a set of possibly infinite lists over the element type. And we just define this as the branches that go through the root of the tree. How do we define the branches that go through a node? We take the tree and we take the address of a node, which is a list of naturals. And this should also, again, return a set of possibly infinite lists. And the easy part of this is actually to just return some addresses and then map them to the actual branches. This is not too hard to do. And this map function on sets is also kind of easy to define. You just say there exists an element such that the mapping of this element is the right thing. And the element itself occurs in the original set. All right. And the key thing is, though, to define the addresses that should go through this. If you first think about it, you might also think that this is super easy. So the addresses that go through a node is now just a set of really infinite lists, which is just the infinite lists which start exactly with this list of naturals, essentially, which is working out kind of okay. And I've been using that for a long while like that, but there's a slight problem with that maybe. So let's look at our tree example again, and let's ask ourselves, what should be good branches or valid branches in here? So for example, if we look at this one, let's just assume the dots continue with some sum, or might at some point have the first child to be none. Would you think that this is a valid branch? Show of hands, maybe. Okay, some people think it is. Let's look at a different branch. Should this be valid? Okay, there's no one saying it should be valid. I agree with that, but according to the definition from before, it would be, right? So this wouldn't make much sense. So we want to adjust our definition a little bit and say that the address that we're considering should be maximal, right? And how we do this formally is we say that the address, the infinite list of naturals, is maximal if the branch is not infinite. So if there is a none occurring somewhere, then on the same level, the first child of the parent node should also be none. This then would make sure that if there would have been another branch where we can continue, then we would have needed to take this one in principle, right? And this is a little ugly to write, but it works as intended. And this is actually nice for my little chase library, coming back to that quickly, because this ensures that in this chase tree thing, if I take a branch out of that chase tree, then this is really a proper chase branch, right? This depends on the exact definitions, of course, and I'm not going to go into this. All right, we have branches ready, so now we can define or, well, state Koenig's lemma and try to prove it. And I'm not going into every detail, but just going into the key aspects because I don't have enough time. And I just put a little crown because König means king in German. I don't know if you know, but yeah. Right. So to state this theorem formally, the hopefully somewhat canonical name would be branches finite of each branch finite, something like that. We take our finite degree, possibly infinite tree, and we just say, if for each branch in the tree there is something which is none, so it is finite, then the set of the branches of the tree that we just defined earlier is finite. And the key idea is to go by contradiction and just assume that there would be infinitely many branches, but then show that you can find a path through the tree such that every node that you take in this branch has infinitely many branches going through it. And by that, you can then show a contradiction to every branch being finite. So what we want to show as a sub-result is exactly this. There exists this infinite list, this infinite address list, basically, such that every node that we take in there has infinitely many branches going through it. And we're going to define this in this way, right? It's just a function from the naturals into something, and we're going to pick the nodes in this branch by a function called infnode here. And we do this for every depth in the tree, we pick one node. And this picking is a little bit tricky, right? And this is why this is a non-computable definition, because internally it's using classical choose. And this is the easiest way to find this to work out, as I am hopefully able to explain in a little bit. So this just takes a depth and the proof that there's really infinitely many branches in the tree, and then returns a suitable node for the depth we're looking for, just meaning that the length of the returned node address is exactly the depth. And of course, the main property should be that the branches going through that node are infinitely many. And the crucial property that we need for this, the formal statement is a little bit tricky, but we just want that this definition always extends the previous node that we picked in the depth before, right? So it should really be a continuous address through the tree and not pick random stuff everywhere. So this is something we crucially need, and this is also why we made the previous thing into a non-computable definition and not just proved existence of such a node, because then we couldn't really work with the previous thing in a nice way. At least I didn't see how this would work. And this also makes kind of sense because after some Googling around, the proofs of Koenig's lemma that you would usually find would require at least some soft version of the axiom of choice. So this is kind of reflected here in this non-computable definition. And once we have that, those are the essential ingredients to prove the actual statement. And if you're interested in the details, you can, of course, look into the repo to see how this fits together. And for the chase trees, we just get the corresponding result for that, which is nice. So if every branch in the chase tree is finite, then the whole chase tree is, which is what we like. And that should be all from my side. Feel free to, well, talk to me, chat with me, look at the formalizations, point out which stupid things I made in the code. And yeah, right. Thank you.